Welcome to our next lesson. 8.3 deals with similar polygons, and we're going to learn about some properties of similar polygons. Now, in this diagram, we have two similar triangles. Triangle ABC is similar to triangle DEF. So you can write a similarity statement very similarly to how you'd write a congruence statement. You want to make sure that the order in which you write the vertices of your polygon corresponds, and instead of using the congruent sign, you're going to use a tilde, and that's the sign that we use for similarity. Earlier in the chapter, we talked about how similarity transformations preserve angle measurement, so corresponding angles are going to be congruent. Additionally, they also enlarge or reduce side lengths by a scale factor of k, like our dilations, so corresponding side lengths are proportional. Here we have two similar triangles, and I'm going to write down the corresponding angles. Notice that the angles that are corresponding to each other are congruent. So these are the pairs of angles that are corresponding and congruent. We also know that the lengths are proportional. So when you take the ratio of the corresponding sides, for any pair of corresponding sides, when you take the ratio, it will give you the scale factor. Notice KC divided by C, you get K. KA divided by A, you get K. KB divided by B, you also get K. So the ratios are all going to be equal. The ratio of all the corresponding sides will be equal to your scale factor K. Note that the similarity statements will tell us which sides and angles are corresponding. So if you look over here at our original similarity statement, A and D are first, so they are going to be congruent to each other. B and E are in the second place, so they will also be angles that are congruent to each other, and C and F are in the third place of the statement, so they were also going to be congruent. So that's how you can use the statement to figure out which angles are congruent and which sides are corresponding to each other. Right, so again, similarity statements tell us which angles and sides are corresponding. We're going to start with example 1, where we are going to be given a similarity statement, and we are going to find the scale factor, list the congruent angles, and we're going to write the ratios in a statement of proportionality. Now, a statement of proportionality looks very similar to the ratio that we got here, so you want to write the three ratios and set them equal to each other. We're going to start with example 1a. In this diagram, triangle RST is similar to triangle XYZ. We're going to find the scale factor from triangle RST to triangle XYZ. So when you're asked to find the scale factor in this manner, the from part, this is like your original, this is where you're starting from. The to part, this is our new, this is what we are going to dilate into. So we're starting off with triangle RST, and we're going to find the scale factor to get to triangle XYZ. Since we're going from bigger to small, our scale factor is going to be less than 1. Whenever you're going from smaller to bigger, so if you're going from small to big, then it's going to be greater than 1. All right, so let's use the corresponding sides to find the scale factor. RS and XY are corresponding to each other, and we can tell that from the similarity statement. So I'm going to set a proportion to find the scale factor. Recall that to find the scale factor, we take new divided by original. So our new is this XY. This is what we want. We're going to divide it by what we started with, RS. So setting up that ratio, I get 12 over 20, and this is going to simplify to 3/5. Now for similar polygons, this ratio has to occur for all the corresponding sides. So we can check that. So ST and ZY correspond to each other. We get 18 over 30, which also reduces to 3/5. And lastly, we just want to check the last pair of sides, RT and ZX. Technically, you don't need to find all three, but I just wanted to show you that all three pairs of sides do have the same ratio, so it doesn't really matter which one you start off with. And we can only tell this for sure because we know for sure that the triangles are similar already. If you don't know if the polygon is similar, you need to check all the sides to make sure that the ratio is consistent throughout all pairs of sides. All right, so here Just testing one side is good enough. We have a scale factor of 3/5. Next, we're going to list all the pairs of congruent angles. Since we have the similarity statement, we can just list the angles that are congruent to each other. So recall, the first angles will be congruent, second, and third. So I get that angle R is congruent to angle X, angle S is congruent to angle Y, and angle T is congruent to angle T. All right, lastly, we just have to write the ratio of the corresponding side lengths in a statement of proportionality. So this is going to look very similar to the ratio of corresponding sides that we got originally in our notes. So I know that XY and RS are corresponding, ZY and ST are corresponding, and XZ and RT are corresponding. So I'm going to set those ratios equal to each other. And we can see that they are equal from earlier. This is the statement of proportionality for example 1. XY over RS is equal to ZY over ST is equal to XZ over RT. I'll let you guys try B on your own. Next, we'll be finding corresponding lengths of similar polygons. But before we do that, we need to note that if two polygons are similar, then the ratio of any two corresponding lengths in the polygon will be equal to the scale factor. This is the fact that we're going to use to solve the next problem. For example 2, I'll be giving you two similar polygons, and you'll need to find the value of x, which is going to be a missing side of the polygon. In order to do that, we are going to set up a proportion to solve for the missing length. So it is similar to writing the statement of proportionality that we have over here, but instead of writing a proportion for all three pairs of sides, you only need two. So you want to use a ratio of two sides that you know for sure, and then you also want to write one ratio with your missing side length and the corresponding side. Here I know that EF corresponds with NP, so I'm going to write that ratio as x over 30. You could write 30 over x as well, but when you write your next ratio, you want the order to be the same. So then I want to use another pair of sides that I know both lengths for. So for example, I could use DF and MP, or I could use ED and NM. It doesn't matter which one you write, but the order in which you write the ratio matters. So since I started with a length of DEF on top, for the next ratio that I write, it has to be one of these lengths from DEF that should be on top, and then from MNP on the denominator. So I'm going to use a DF and MP. You could use ED and NM as well. So DF over MP will be 20 over 24. So from here, if you notice that you can reduce the ratio that you get, then you should do that because it'll simplify your steps later. 20 over 24, that will reduce to give me 5 over 6. Right, and again, you don't really need to reduce it, but that's just my preference. I always like doing the simplification before rather than after. Once you get here, you're going to cross multiply. So x times 6 is 6x. 30 times 5 is 150. Then we just want to solve for x. Divide by 6 on both sides. X is equal to 25. Let's do that one more time. We're going to look over at B. We have triangle GHM is similar to triangle HKL. We need to find the length of KL. KL corresponds with this side right here, HM. We can tell that from the similarity statement. KL and HM are in the same positions. So I'm going to write a ratio of KL over HM. Again, you could do 12 over x. Just the order that you write for the next ratio matters. So keep that in mind. We want to write a ratio with two other sides. I'm going to use KH and HG. KH has a length of 15, HG has a length of 10. So I'm going to get a ratio of 15 over 10. I'm going to reduce 15 over 10 to 3 halves, and then I'm going to cross multiply. After I cross multiply, I get 2x is equal to 36. X is equal to 18. I'll let you guys try C. Okay, so our rule for corresponding lengths also applies for lengths that aren't the sides of your polygon as well. So if we look over here, we have a perpendicular bisector for the triangles TPR and triangle XPZ. So because the two triangles are similar, the perpendicular bisectors are also corresponding lengths, and they will also have a ratio that is equal to the scale factor. So we can use that fact to write a proportionality statement. P.S. I don't know what that is. I'm going to call that x. So adding the two sides together to get the whole length of this triangle. 6 plus 6 is 12. 8 plus 8 is 16. Now I'm going to write the ratio. So x corresponds with 20. That's going to be equal to 12 over 16. I'm going to reduce. X over 20 is equal to 3/4, and then cross multiply. 4x is equal to 60. Divide by 4 on both sides. X is equal to 15. So the steps are nearly identical to the examples that we did before. So I'll just let you guys try B and C on your own.